Okay, so digital imaging, at least for like still image X-rays, is going to come in two varieties. We're going to call them DR and CR. Okay, so we're going to focus on those types. We're going to talk about DR first, which is going to be the more common one in any new equipment that's coming out, and then CR second. But as we list them, CR's first on this page here. So what do these words mean? CR means computed radiography. Now that might seem like it refers to all types of digital, but it's a very specific type of digital. It was the first type of digital radiography to be used. This is often just called filmless radiography because we use a cassette still, and that cassette has to be taken from the place where the image is captured on the X-ray table or in one of the wall or table buckies, and has to be taken physically to a processor. And there's a plate inside of the cassette that has to be removed from the cassette case and processed through an actual reader. So there's no direct connection to the processor and must be physically carried and inserted into a reader. Contrasting that with DR, DR stands for direct radiography, or as they say, direct capture radiography. And we'll learn in a moment here that there are different types of that even. But importantly, it does not require an image receptor to be carried to a processor that is separate from where the exposures are being made. Right? The cassette can just stay in the X-ray room, on the tabletop, in the table bucky, or on the wall bucky. And in some cases, it is built into the table bucky or the wall bucky, and you actually cannot remove it. So there's plenty of different types of these things. I've worked with both, the ones that have been attached physically, like you'll see in a moment, and others that are like a wireless setup where you can actually, it looks like a real cassette, but it will communicate directly with the computer wirelessly. So image receptor is connected directly, electrically or electromagnetically, as in wirelessly, Wi-Fi type setup, to the processor. The oldest, the original type of DR came with a fixed unit. There was no cassette. It was just the bucky itself was the receptor, and it had a physical cable running to the computer. The next generation let you have a cassette, but the cassette was still connected by cable to a computer. And then the newest generations are the wireless type. Those are the best ones, and they get very expensive too. Which is, you'll learn this when you go out there and you start handling the equipment, because they will make a point of telling you how expensive these cassettes are. I remember when I first learned on DR, a brand new DR system, they were telling me the cassettes themselves cost about $100,000, just a single cassette. So and that was wireless, DR, communicated directly with the computer. Used for mobile radiography, and then of course the stationary X-ray machine radiography. So we're going to refer to that as DR or cassetteless radiography, because oftentimes it doesn't have its own cassette. So this is an example. Let's zoom in a little bit. This is an example of a cassetteless unit. What this is, if you look you'll see the horizontal actual image receptor. You'll notice that there's two circular and one rectangular dark cells on that plate there, and those cells are maybe you can tell me, what are those cells representing? Those circles, and those two circles, one rectangle. What are those showing us? Something we talked a little bit about last time. What's the primary way digital controls the exposure to patients? No idea? Everything we talked about last time is gone? Okay. So just say what you think they are.
These are the three little spots on the bucky that basically control how much exposure a patient is getting per type of X-ray that they're getting.
Great.
Basically, it's just like a little sensor. Once it gets enough of the exposure that it's its own limit, and it shuts off.
Great. That's fantastic. So what is it functioning to control? Is it functioning to control KVP, MA, or time during the exposure?
All of it. Well, no, actually, it's time.
Time.
Exposure.
Right, time, and then ultimately mass, right, the total mass number. Thank you. That was pretty good. So what they are, right, as he said, they they detect exposure, right, and stop the exposure when it's enough, right? These are called ion chambers, okay? Ion chambers are small little radiation detection chambers that when the X-rays strike them, they're able to generate an electric current, right? That electric current, we have a preset current quantity, preset current, that when we get to that current, the exposure timer is shut off, right? We can activate all three of these cells to all work in unison. We can activate the two in this case circular, often they're all rectangles, but in this case those two circular ones, we can activate those two, or just the single middle rectangular cell. And they'll that's the type of the type of control this is. We call it automatic exposure control. This is really common of digital systems because, as you'll learn in a little while, digital systems are they have what's called a wide exposure latitude, which means that, you know, if I told you the mass was the correct mass for an exposure was 10 mass, you could in some cases get away with using 8 times that, right? So 80 mass or more, right? Um, and still achieve an appropriate image. This automatic exposure control is a way of preventing the X-ray tech from overexposing the patient and being a little more accurate with their exposures, essentially, is what AEC is designed for. So when you see those cells, that means that the unit likely has AEC available, and it can actually be turned off at the control console where you're making your exposures from. You can actually turn it off, turn it on, activate the individual cells. But this is a wall bucky. This is a special type of wall bucky that can actually go from being vertical to horizontal. Okay. So what this will work great for is it'll work great for doing all of your upright studies, chest and upright spine studies, shoulders, humerus, all those upright studies. So, you know, and of course we can do weight bearing studies of the lower extremities too. But then the whole bucky will turn horizontally so that you can do your regular tabletop studies. This would be in place of the regular tabletop studies. So that is an example of a DR bucky system where there is no cassette. There's nothing to remove from that bucky. It's just built into it. Okay, so yeah, so for DR, the radiographic table or chest board, in this case, houses a permanent array of miniature radiation detectors. These are different, well, as I'll talk about, these are different than those three little cells, the circular and rectangular cells that I was talking about. What we're going to be talking about here is that in this detector plate, there are, like pixels in a computer, there are detector cells, or what we're going to call detector elements, embedded in that plate. If the plate is 17 by 17 inches, then there's detector elements along that whole matrix, that 17 by 17 inch matrix. So disadvantages to these fixed type systems, they're not super flexible. I mean, you pretty much have to put the patient in the position on that bucky. And for example, like in tabletop exams, you can turn the cassette just sitting on the table. You can rotate the cassette to make it in line with the patient. You can turn the collimator box to make everything line up. With this, you just can't do that. So there's a difference in how the systems are able to be used. And often DR has less flexibility of use than CR with just an actual cassette will have. Okay, so these detector elements, they're showing you sort of a cartoon of these detector elements here, which we'll break them down in just a minute. But to talk about these detector elements, we have to talk about what keeps them from being smaller, okay, or what originally kept them from being smaller. Because as you learned last time with pixels, right, the smaller your pixels, the better the spatial resolution you have is, right? And so if you were going TV shopping and you were picking out TVs and you wanted to get a 60-inch TV, right? You would pick the one that in that 60-inch, frame had more pixels than the other one, right? The other option that you're considering. So, and you know that because it's going to get you a better image, we call that spatial resolution. Well, with DR, your actual receptor has what we're going to, as I said, call detector elements or DEC cells, right? These individual little squares that detect radiation are effectively going to be pixels on the computer screen, and the smaller these detector elements are, the smaller the structures you can detect, the smaller the structure you can see. For CR, which we'll talk about later, and old film radiography, there was no real limit to the spatial resolution that your cassettes could achieve. You were only limited by the computer screen that you're viewing on, or with film, you were limited by the actual focal spot size of the X-ray tube. Remember we talked about focal spot size a lot in radiation principles of exposure. Those were your only real limits to spatial resolution. In DR, your limit to spatial resolution is primarily one of two things: the detector element that we're discussing and the pixels used on the actual monitor you're viewing from. So this first one talks about DEC cells here. So two hurdles had to be overcome to implement DR to have it be at least as good to the eye as film or CR is. So one, the development of inexpensive detector elements, DEC cells, and the miniaturization of these DEC cells to make them smaller than the human eye can detect, right? You have a hard time, like when I look at my computer screen, I'd have to use a magnifying glass or something like that to zoom in close enough to see an individual pixel, right? Same thing with DEC cells. They had to be small enough to where to our eye they don't look apparent. Everything looks like a nice continuous image. So modern DEC cells, the size for a modern DEC cell is about 100 microns, but roughly 1/10 of a millimeter, or about 1/10 the size of the head of a pin. So they're extremely small nowadays, which makes them smaller than the threshold for the human eye, and we can't see them, right? So they're small enough now. They are still larger than any detector element on a CR cassette or the crystals on a screen film cassette. So they're still bigger. You still can't get as good of spatial resolution on DR. So this is a theme, okay? DR has lower spatial resolution than CR. CR has lower spatial resolution than film. Film will always have the highest spatial resolution. CR is a little bit worse, and DR is a little bit worse. The advantage to why would you use the DR systems, right? DR has a much wider dynamic range. Remember dynamic range from last lecture? What was dynamic range associated with? Grayscale, right? And so dynamic range, right, was the so remember we talked about bit depth, dynamic range, and grayscale, right? Bit depth was in principle how many shades of gray could your computer achieve, right, for an X-ray image. Remember, it's color on some things, but in X-ray we talk about shades of gray. So bit depth is, in principle, how many shades of gray can your computer achieve. Dynamic range is how many shades of gray are made available to the computer to use, right? And grayscale is how many shades of gray are actually being used on the image, right? You're always using less dynamic range than your bit depth, and you're always using less of a grayscale than your dynamic range would allow you to, just simply to save processing time. Remember, the human eye at any one time can only identify 32 different shades of gray, right? So giving you 4,000 of them is useless because the human eye, the thing we're using to evaluate images, can't do that. Okay, so these detector elements are the thing, right? That's going to show you the shades of gray. And with DR, the dynamic range, the actual number of shades of gray that you can use is much wider than CR, and is much wider than film. So while DR can't give you as good of spatial resolution, it gives you a wider dynamic range, more available shades of gray. We would say instead of spatial resolution being better, we can say that DR has a much better contrast resolution. We can show more shades of gray on DR. So that's why when you look at DR images, they look better. They look better than film. But in all actuality, their resolution is not as good, but their contrast resolution is much better. So the theme is DR, the best type of digital, has lower spatial resolution than the best type of film, but film has a much narrower contrast resolution, where DR has a much wider contrast resolution. So I can show more shades of gray on DR than I can with film. And CR is sort of somewhere in the middle. Okay, so these detector elements, they get arranged on a plate into what's called an active matrix array, a flat layer of elements, each containing its own what's called thin film transistor. Don't worry, I'll define terms in just a little bit. Okay, so great. So now we have a little bit about why it was difficult originally, and now we have the size that we actually use for our detector elements. So let's just define, make sure everyone's on the same page. Voxels, dexels, pixels, right? These terms that mean the end of it always means something element, right? So volume element, detector element, and picture element. Well, pixel refers to the elements of the image, right? The individual pixels on the computer screen. Dexels are the detector element used on the actual active matrix array, the actual image plate. You know, this dexel that I'm pointing at now with the laser pointer, the top left one, will be the top left pixel on the computer screen, right? So they'll, in spatial terms, they'll be in the same spot, but they are a different thing. The detector element is on the cassette, where the pixel is on the computer screen. Now, voxel, actually I'm going to go right here. Voxel is, imagine the X-ray beam, right? The X-ray beam is going to pass through the patient and hit the image receptor, right? The X-ray beam has passed through a three-dimensional patient. So the spot on the little dexel on that image receptor that's getting hit with the radiation, that little dexel is going to carry the information about a three-dimensional column of tissue. That three-dimensional column of tissue is called a voxel. Okay, it stands for volume element, because volume is length times width times height, or in other words, three-dimensional. So again, X-ray beam has to pass through a three-dimensional structure and then hit one of these detector elements. So on the detector element, the information that's represented there will represent a three-dimensional structure. That's all that you need to know about a voxel. Dexel, so to form a DR image, information from different voxels within the patient are collected on the dexels of the imaging machine, and then computer processed to become pixels on the computer screen. Okay, so these DR systems with their dexels, we have to understand, because you'll be asked this, just so you know, you'll be asked to understand what they are. These detector elements have three components, okay? So the three components are, number one, the detector surface. Now what you should know is, what you're looking at, right, is the face of the dexel. The dexel's face is not entirely detector surface. Part of the face of the dexel is occupied by two things. One thing is called a capacitor. The other thing is called a thin film transistor. So let me explain. The dexel detector surface is made of something called a semiconductor. Hopefully you guys remember what a semiconductor is. You don't have to tell me which ones we're using here, but what does it mean to be a semiconductor? What do you think, Francisco?
Semiconductor is a little type of like, I don't want to say maybe metal's not the right word, but a little object that can help transfer energy, and keep it basically like, keep it from going out of it, like it'll be wrapped in some kind of plastic, or not plastic, like rubber. Basically,
Okay.
it can help you control the flow of electricity running through.
I like when you said it helps you control the flow of electricity. Good. Okay, so let's contrast semiconductor with conductors and insulators. Okay, so with regard to electric current, what is a conductor? Hey, Josie.
Allows electricity to flow better.
Good. Good. So, conductors allow electricity to flow freely. What's electricity? Brittany, what's electricity?
I mean, I know what it is, but I can't explain it.
Well, what is it to you?
Like electricity, the light.
Right, like I know it when I see it kind of thing, right?
Yeah.
So, good. So you got to be able to define it, right? So let me be very clear for the, I don't know how manyth time. Electricity is the flow of electrons along the surface of a conductor. That's all. Okay. Electricity is electrons flowing. Okay. What has electrons in them? Everything. Okay. All matter, all atoms have electrons. Electrons are bound to their atoms, right? That's how an atom works. Some materials have loosely bound electrons. So when you apply a potential difference, a voltage potential difference to a conductor, the electrons in that conductor will hop, 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 hop along the surface of the conductor, and electricity will flow. Okay. What types of things conduct electricity easily? Copper conducts electricity easily. If we had like unlimited money, we would just build everything out of gold, right? Gold is one of the best conductors, right? In fact, gold is used in some electronic devices, and it actually can. Some people will actually take time to go and like harvest the gold from electronic devices because it's there. And okay, huh?
That's how they made the Olympic gold medals for Japan.
Is that right? They took it out of like
They recycled
cell phones. Yep. So yeah, exactly. And they're used in the little microprocessors because gold is a fantastic conductor. Okay, great. So there's conductors. Conductors allow electricity to flow easily. What's electricity? Well, electricity is flowing electrons. Electrons moving along the surface of a conductor. What's an insulator then?
Tightly bound electrons does not allow the flow of electricity.
Yeah, does not allow the flow of electricity. Why? And as Parrish correctly said, because the electrons in insulators are tightly bound. They don't want to go hop, hop, hopping along the surface of the material. So a conductor allows electricity to flow easily. An insulator does not allow electricity to flow easily. What's a good example of an insulator? Rubber, glass, dry wood, those are all great insulators, right? Electricians, they wear shoes made out of glass. No, I'm kidding. They wear shoes made out of rubber, right? And their car. You look at the electric trucks, the electricians' trucks. They have big, thick rubber tires, right? They're insulating tires so that they don't ground themselves and shock themselves. Okay, so you have conductors, you have insulators, and then in the middle, you have a class of materials called semiconductors. Semiconductors Semiconductors allow electricity to flow, but not under all circumstances. They allow electricity to flow when specific kinds of, for example, when specific wavelengths of light hit them. Okay, X-rays are a type of electromagnetic wave like the rest of light, okay? So they will allow electrons to flow when specific photons hit them, specific energies of X-rays hit them. Some semiconductors will allow electricity to flow only when a small voltage has already been applied to them, but in a very specific voltage, okay? So semiconductors, what you need to remember is semiconductors allow electricity to flow under special circumstances. So not under all circumstances, right? Copper is not a semiconductor because it allows electricity to flow anytime you apply a voltage to it, anytime you apply current, rather a potential difference to the copper. Okay, so you don't build any electric device is not built with a semiconductor, only very specific kinds like the kinds used in computers and such as the ones used in these detector elements. So the detector surface, shown in green, is made of something called a semiconductor. There's two materials you're going to have to memorize, okay? They are amorphous selenium, which I'll define them later, don't worry about it too much right now, and amorphous silicon, okay? You guys probably have heard of silicon before because there's a place called Silicon Valley, right, where all the computer advancements are being made. But those materials that I just named are called semiconductors. They're the class of material called semiconductors. Good. The detector surface is a semiconductor. So when X-ray photons hit the detector surface, electric current is generated, okay? And based on the wavelength of the photons, and the quantity of them, more or less current will be generated in the detector element. Okay. So, and if no photons hit the detector element, then no current is generated, right? So this is how we're going to be able to know how much exposure is being reached at any individual detector element, because more or less current will be generated based on wavelength and quantity of those photons hitting the detector. The second thing in this is called a capacitor. What you need to know about capacitors are, they're like a battery. Okay, now this says microscopic capacitors, so they're teeny tiny, but capacitors will store electric charge for a very short period of time. If anyone's ever dealt with car audio, they know about, you've heard of capacitors. Some cars will actually use capacitors along with their car battery to do the ignition, to turn on the car, to actually spin the starter and turn on the car, because some cars have like high performance engines that require extra oomph to turn them on, and capacitors can store electric charge and then let it all go at one time. Okay, so in this case, when radiation strikes the surface of the detector, some electric current is generated. That electric current is stored in the capacitor for a very short period of time. Once all of those detector elements have gotten their exposure and the exposure is turned off, every detector element has an amount of electric charge stored in the capacitor. Then so each one of these stores electric charge, the capacitors do in all of these detector elements. Then when it's their turn to send, each one of these takes a turn sending the signal to the computer. When it's their turn to send the signal to the computer, the thin film transistor will switch on and let the current out of the capacitor and to the computer. Okay, and the computer reads them one at a time. And it knows which one it's reading at any one time, and it puts the exposure for that in a specific spot on the screen, and that specific spot is a pixel, and each pixel gets a value based on the amount of exposure given at each one of these detector elements. Does that make sense? Okay, I know we're dealing with a lot, sort of really technical stuff today. Okay, there's two ways this can be done. We're going to call them direct conversion and indirect conversion. So two types of DR. So direct conversion. Direct conversion, well, what are we converting? We're converting X-rays into electric current, right? So the semiconductor detection surface of a DEXL is either sensitive to, those semiconductors, either sensitive to X-rays or visible light, which I'll explain in a little bit. Detector surfaces that are sensitive to X-rays are made of a semiconductor called selenium. The spelling is listed here. That's the direct conversion systems. Those are the direct conversion systems. X-rays pass through patient, X-rays strike detector surface, and on the detector surface, a current is generated when the X-rays strike the detector surface. Indirect conversion, the other option for DR systems, will take the X-ray beam exiting the patient, interact that X-ray beam with a crystal, special type of crystal, and then let that crystal emit visible light, and that visible light is what exposes the detector element. So it's an indirect way of getting the exposure to the detector. Those types will use a material called silicon. Okay. So the next thing, so we'll go delve more deeply into those in just a moment, but we need to talk about what's called something called detective quantum efficiency, because it's sort of this weird idea, but it's not that hard to understand. People think it's hard to understand because it uses the word quantum in it. It's not difficult at all, I promise you. Okay, so detective quantum efficiency is effectively how efficiently the detector can convert X-rays into electric current. Okay. And this is based on something called the fill factor. The fill factor is how much of the detector surface is actually detector material. Okay, so let me show you. Let's go back, just go back one slide. So you notice this whole square representing one decel, representing 1/10 of a millimeter square on the detector. Only the green areas are sensitive to X-ray. There is a portion, a chunk, that is used by the capacitor, and a chunk of that surface that's occupied by the thin film transistor, the switch. So the problem is that currently we cannot make the capacitor or the thin film transistor any smaller. Okay? But if you had a smaller decel, you in principle could get better resolution, right? The smaller the decels, the better resolution. However, all decels need a thin film transistor and a capacitor. So if you try and take the TFT and the capacitor that we have now and put it onto a smaller decel, then less of that surface will be occupied by actual detector, and you will lose resolution. So right now, that decel that's about 1/10 of a millimeter in size is as small as it can ever be until we can further miniaturize the battery and the switch. Okay. With a smaller percentage of detection surface, an increase in radiographic technique is necessitated. There we go. And you lose resolution. You have to have more exposure to make the more exposure to actually get the right level of exposure at the receptor. And so it's no good. We are sort of stuck with the size that we have now, which means that we are limited in our spatial resolution. Okay? We will at this point, cannot at this point achieve greater spatial resolution than we have currently. Whereas CR and film have in principle no real limit to their spatial resolution. DR does, and it's the size of these actual components that are going into the decel. Okay, so these images these cartoon images that you've been seeing are the decel from the front, the face of the decel. Okay, what the X-ray beam would interact with. Okay, the next thing I'm going to show you is the decel from top to bottom. Okay, so the top of the image here, the top of the image is the face of the decel. Okay, the bottom of the image is the back side of the decel. Okay, so we're looking from top to bottom, sort of a cross-section image of the decel. Okay, so the way it's going to work is, remember, semiconductors allow electricity to flow. And what is electricity flowing? Electricity is electrons moving along a conductor. Okay, so these semiconductors have to be, hi. Oh, thank you, the lab, thank you. These semiconductors have to be sensitive to the type of radiation that's going to hit them. In this case, it's selenium, and you'll know it's selenium because if you look on the actual gray part of the detector, it says A-SE, amorphous selenium. Okay, amorphous just means the material is not in crystal form, more like a powder. But in any case, selenium will free up its electrons when X-rays strike it. Okay, so X-rays pass through the patient. They ionize. What's ionize? What does the word ionization or ionize mean?
Is it like charging?
It is. It's charging the particle, right? X-rays ionize the atoms of selenium. Okay, and when they do, as I said, the electrons will be freed from the atoms. Okay. So the selenium is struck by X-rays. The electrons, which have a negative charge, and the rest of the atom, which has a positive charge, separate. The atoms become ionized. A small amount of current is run through the face of the detector element, so the electrons are attracted to that. The electrons move upward, as you see the little negative charge bubble showed moving upward. The bottom surface has a small negative charge. Okay, that small negative charge attracts the positively charged ionized atoms to it, and we get an amount of current flowing. Okay, that current flow, that electron flow, that current, is detected and stored by the capacitor until all the DEC cells have gotten their exposure, and the computer needs to give the imaging plate needs to give a readout to the computer. In which case, one by one, row by row, all of the DEC cells, the TFTs, will begin to switch and let the current out of the storage capacitor to the computer in a line, in a serialized line, and the computer reads one DEC cell at a time, reads the current that got to each DEC cell one at a time. So the top electrode attracts freed electrons to drift upward. The DEC cell electrode down at the bottom has a negative charge applied, attracting the positively charged, what in this case they like to call holes, which are just ionized atoms, to drift downward. The freed electrons will move, the charged atoms will move. The positive charge from the lower electrode is accumulated in the capacitor. So the lower electrode has a negative charge running to it, but all of those positively charged atoms are moving downward and develop a positive charge. That positive charge is again stored in the capacitor, and then one by one, each DEC cell will send its current out to the computer. So the array of DEC cells is crisscrossed by wires called gate lines and data lines. Gate lines are controlled by something called an address driver. The address driver controls the order in which DEC cells read out to the computer, so that they don't all go at the same time and they don't go out of order, right? So for example, DEC cell row 1, column 1 goes first, and then row 1, column 2 second, and then row 1, column 3 third, and then row 2, column 1, row 2, column 2, row 2, column 3, and so on throughout the entire active matrix array. One DEC cell at a time does its readout to the computer. Okay, so each DEC cell receives an amount of X-rays striking it, building up a current. That current is stored in the capacitor. When all the DEC cells, when the exposure is done and all the DEC cells are charged, they will read out in rows and lines one by one to the computer. The computer knows the order that they're coming in and will assign them a place in space on the computer screen. That's effectively how direct conversion works. X-rays ionize the selenium charges the capacitor, and the capacitor sends its signal to the computer by serializing one by one which DEC cell goes first and second and third and fourth and so on. Okay, so now you have the everything you need to know how DR actually gets it done, gets it started to go to the computer. We have to now add on something called indirect conversion, which indirect conversion is another option for DR, and it gives an extra step. Okay, you might ask, well, why would you have two different types? It's cost. Their costs are different, and they were developed at different points in time. Okay, so for example, indirect conversion was developed first. Okay. So we're going to talk about indirect conversion now. We're definitely going backwards, by the way, in historical development. DR, direct conversion, is newest. DR, indirect conversion, a little older. And then CR, which we'll get to in just a little bit, is even older than that. Okay, so again, but you may come across both. For functional purposes, there's no difference.